Good afternoon, my name is Jion Park, and today I'll be giving a talk titled Gaussian Splatting Meets Robotics. And I want to talk about how Gaussian splatting is entering robotics, and more importantly, what still seems missing. Gaussian splatting has already become a major representation in computer vision and graphics, but its role in robotics is still being explored. So I will first look at the recent trend at ICRA 2026 and compare it with last year ICRA and this year CVPR. This gives us two views that how fast Gaussian splatting is growing inside robotics and how the robotics community differs from the vision community in the way it uses Gaussian splatting. After that, I will share some observations from conversations with researchers working on Gaussian splatting and robotics. These discussions helped me understand that although Gaussian splatting is becoming popular, the community is mostly focused on mapping, active reconstruction, semantic maps, and simulations. Robust Gaussian splatting-based navigation is still not receiving as much attention. Then I will explain why I still think Gaussian splatting is valuable for robotics. The key idea is that a Gaussian splatting map can act as a renderable interface. From one map, a robot can query different sensor views, resolutions, and modalities depending on the task. Finally, I will summarize the main research direction in Gaussian splatting-based robotics and end with the main takeaway that photometric Gaussian splatting is powerful, but it is not automatically planning ready. I think this gap creates interesting opportunities for robotics research. Before going further, let me briefly recap what Gaussian splatting is. In Gaussian splatting, a 3D scene is represented as a set of explicit Gaussian primitives, and each Gaussian has parameters such as position, covariance, opacity, and appearance, and potentially additional attributes depending on the task. The first key point is fast rendering. Gaussian splatting is designed around a GPU-friendly, tile-based rasterization pipeline. It projects Gaussians onto the image plane, sorts or composites them based on visibility, and rasterizes the image in parallel. This CUDA-friendly architecture is what enables real-time, photorealistic rendering. And the second key point is differentiable optimization. The rendered image is differentiable with respect to the Gaussian parameters. So during training, we render an image from the current Gaussian map, compare it with the observed image, and backpropagate the image loss through the renderer. By the chain rule, the image level error becomes gradients on the Gaussian parameters. So the core idea is quite simple that Gaussian splatting combines fast GPU rasterization with gradient-based parameter optimization. This is why Gaussian splatting became so influential. It is not only fast to render, but also directly optimizable from image supervision. For robotics, this is especially interesting because the map is explicit, renderable, and can potentially be connected to perception, planning, and control. So the next question is Gaussian splatting actually becoming more important in robotics? To answer this, I compared Gaussian splatting related papers at last year and this year ICRA. At ICRA, Gaussian splatting grew from 50 to 75 papers in a year. So Gaussian splatting is actively gaining share and moving from a niche to a mainstream scene representation in robotics. But if we look at what these papers are about, the picture is quite clear. SLAM, mapping, and localization still dominate at around 32%, by far the largest slice. Semantic and language-guided 3D Gaussian splatting are creeping up, and applied areas like autonomous driving are growing, but they remain comparatively small next to the SLAM core. So while the frontier is slowly broadening, the center of gravity is still firmly on mapping and localization. After looking at how Gaussian splatting is growing inside ICRA, I also wanted to compare ICRA 2026 with CVPR 2026. The reason for this comparison is that CVPR and ICRA shows two different stages of the same technology. CVPR usually shows where the Gaussian splatting methodology is being pushed, while ICRA shows how those methods are being adopted for robotics. So by comparing the two, we can see not only how much Gaussian splatting appears in robotics, but also what parts of the broader Gaussian splatting frontier have not yet fully arrived in robotics. And in absolute numbers, the gap is quite large. CVPR has 217 Gaussian splatting related papers, while ICRA has 74. So CVPR has roughly 3 times more Gaussian splatting related papers. But the more important difference is how Gaussian splatting is used. At CVPR, Gaussian splatting is mainly treated as a methodological frontier. The focus is on expanding the capability of Gaussian splatting: efficiency, compression, real-time rendering, dynamic and 4D scenes, physics, generation, editing, and feed-forward reconstruction. At ICRA, Gaussian splatting is mostly used as robotics infrastructure. This gap suggests a time lag between the two communities. What CVPR develops as a new Gaussian splatting capability may later appear in ICRA as a robotics tool. One example is efficiency. If you look at the bottom right side of this figure, these topics are much more concentrated in CVPR, which means they are closer to the current frontier of Gaussian splatting research. CVPR has many more papers in compression, acceleration, and lightweight Gaussian splatting, while ICRA has very few. This suggests that Gaussian splatting is entering a more mature stage. The question is no longer only whether it works, but whether it can run fast, compact, and in real time. Another trend is that Gaussian splatting is moving beyond static reconstruction. The frontier is shifting toward dynamic scenes, physics-aware Gaussian splatting, semantic, and language-grounded Gaussian splatting. There is also an architectural shift from per-scene optimization to feed-forward and generalizable Gaussian splatting. Instead of optimizing each scene separately, recent works aim to predict Gaussian splatting representations directly using large or generalizable models. So the main takeaway is that CVPR is expanding what Gaussian splatting can do, while ICRA is starting to use Gaussian splatting for robotics. The gap between them helps us see what may come next in Gaussian splatting-based robotics. Overall, research on Gaussian splatting in robotics can roughly grouped into a few directions. First, there is SLAM, mapping and reconstruction, which is still the most common application, focusing on building dense and visually rich 3D maps. Second, we have foundations and rendering, where researchers working on improving geometry, rendering quality, computational efficiency, and compatibility with different sensors. Another growing area is active mapping and next best view planning, where the robot actively decides where to move or look next in order to build a better map. We're also seeing semantic Gaussian splatting and VLA-VLN, which extends Gaussian splatting beyond geometry to create language-queryable scene representations for navigation and embodied agents. Navigation, planning, and localization is still a relatively underexplored area. There are few works such as SplatNav, but robust point-to-point planning directly on Gaussian splatting map is still an open problem. Gaussian splatting-based manipulation is another emerging direction, covering topics like object-centric reconstruction, grasp planning, and affordance reasoning. Finally, there's Gaussian splatting as a simulation platform, where Gaussian splatting is used to generate photorealistic environments for training robot policies. However, when I actually went through the Gaussian splatting related posters at ICRA, I noticed that if we exclude SLAM papers, most robotics-oriented works were centered around active mapping and next view best view planning. That observation led to my main question: if Gaussian splatting is becoming more popular in robotics, why is Gaussian splatting-based navigation still relatively rare? To better understand this gap, I talked with several researchers working around Gaussian splatting and robotics during the conference. I asked them what they were interested in and how they saw the role of Gaussian splatting in robotics, and why navigation did not seem to be a major focus. Among those conversations, one discussion was especially helpful, so I would like to briefly share it here. The researcher I talked with was Maximilian Adang from Stanford Multi-Robot Systems Lab. MSL is one of the groups actively exploring the frontier topics in robotics, where Gaussian splatting is used as a scene representation. Their work includes Gaussian splatting-based simulation, active mapping, semantic scene representations, and vision language navigation. The first point we discussed was why Gaussian splatting-based navigation is still relatively underexplored. My current interpretation is that it sits between the two communities. On the computer vision and graphics side, the main focus is on reconstruction quality, rendering realism, semantic richness, and scalable Gaussian splatting maps. On the robotics side, however, the requirements are quite different. For navigation, we need robust point-to-point planning, collision and safety guarantees, real-time onboard inference, and reliable behavior even when the map is incomplete or degraded. So the issue is not simply that Gaussian splatting is not useful for navigation. The issue is that a photometric Gaussian splatting map is not automatically a planning-ready map. A visually good reconstruction does not directly tell the robot what is free space, what is occupied, what is traversable, or how uncertain the map is. We also discussed the strong baseline problem. In robotics, LiDAR-based occupancy maps and classical planners already work very well for many navigation tasks. So if a Gaussian splatting-based navigation paper only shows that a robot can avoid obstacles and reach a goal, the contribution may look weak. This means the real research question is not, can we use Gaussian splatting for navigation? But a strong question is, what does Gaussian splatting uniquely enable for navigation that classical occupancy maps or LiDAR-based pipelines do not? And the second question is, if Gaussian splatting navigation is underexplored, why is robust point-to-point navigation not getting much attention? From the conversations I had, my impression was that the mainstream direction is Gaussian splatting in robotics is simply heading somewhere else. The focus is less on low-level motion robustness, but more on richer scene representations and high-level robot behavior. For example, Maximilian's interest was quite representative of this trend. Gaussian splatting as simulation, viewpoint planning, exploration, semantic Gaussian splatting for vision-language navigation, and VLA-style policy learning. What these directions have in common is that they treat Gaussian splatting as something to build, enrich, or learn from. In active mapping, the goal is to build a better Gaussian splatting map. In semantic Gaussian splatting, the goal is to make the map more meaningful and language queryable. And in simulation or VLA, the goal is to use Gaussian splatting rendered scenes as training environments. But in all of these cases, Gaussian splatting is not necessarily treated as an actual geometry that a planner can directly navigate through. That is why I think robust Gaussian splatting navigation needs a sharper framing. The question should not be just whether Gaussian splatting can support navigation, but what kind of navigation becomes possible because the map is renderable, semantic, and view-dependent in a way classical maps are not. To summarize, Gaussian splatting is clearly growing in robotics, but it is still mostly used as perception and mapping layer. The dominant directions are better Gaussian splatting maps, active reconstruction, semantic maps, and simulation. These are important, but they do not yet make Gaussian splatting a planning-ready representation. The key limitation is that photometric Gaussian splatting is optimized to look good, not necessarily to support safe robot actions. For robotics, we need more than visual quality. We need free space, collision geometry, traversability, uncertainty, and safety guarantees. So the main takeaway is this, that Gaussian splatting is becoming important in robotics, but the next challenge is to turn it from a renderable scene representation into a task-ready world model for planning and navigation. Before moving to specific research topics, I want to first explain why I think Gaussian splatting is useful for robotics in the first place. What I find most interesting about Gaussian splatting for robotics is that it can serve as flexible, renderable map. The map stores the scene once, but the rendering query can be adjusted depending on the task. One important knob is which Gaussians we render. We do not always need to sort and composite the entire map. By selecting a local region, an object-level subset, a semantic subset, or a dynamic layer, we can reduce the target Gaussian set and make rendering more efficient. Another knob is the projection model. The same map can be rendered through different image formation models such as perspective, fisheye, equirectangular panorama, orthographic BV, or arbitrary ray sampling. We can also change the sampling resolution. The query can be sparse, like a few rays or low-resolution samples, or dense, like a full high-resolution image. Finally, the rendered target can change depending on the task. From the same map, we can render RGB, depth, surface normals, semantic labels, instance information, primitive attributes, or learned features. So the important point is that we do not need a separate map for each sensor or task. we keep one underlying Gaussian splatting representation and change the rendering query. This is why I think Gaussian splatting is promising for robotics. Rendering becomes the interface between the map and the robot. From the same Gaussian splatting map, we can render not only RGB images, but also normals, depth, edges, and even LiDAR-like measurements. We can also render attributes stored in the Gaussian primitives themselves. By defining primitive-level attributes from different statistics, we can visualize and inspect them directly through rendering. The main point is that, if we query it properly, a Gaussian map can quickly provide the information required by a robotic task. So Gaussian splatting is not just a map to visualize. It is a representation that robots can query for task-relevant observations. From this perspective, I started thinking about research topics that our lab can contribute to. The first research direction is to better exploit the representation itself. As I mentioned earlier, most Gaussian splatting maps are optimized for visual fidelity, so we should not assume that they are directly planning ready. For example, 3D Gaussian splatting maps often contain floating Gaussians or ambiguous geometry, as you can see at the left figure, which can be acceptable for rendering, but problematic for collision checking or navigation. This is why more robotics works are starting to use geometry-aware variants such as 2D Gaussian splatting. Since 2D Gaussian splatting represents the scene with surface-aligned Gaussian primitives, it can provide more consistent geometry and well-defined surface normals across viewpoints. From a robotics perspective, this is important because the map should not only look good, it should also provide reliable geometric information that can be used for planning, safety, and interaction. Another direction is to use 4D Gaussian splatting style representations. This is interesting for robotics because robots operate in dynamic environments. Objects move, people move, and the map itself may change over time. In that sense, 4D Gaussian splatting gives us the way to model not only the static scene, but also its temporal changes. However, the main bottleneck is computation. 4D Gaussian splatting often requires much more memory, optimization time, and rendering cost than static Gaussian splatting. So while it is conceptually very relevant for robotics, making it lightweight and real-time enough for onboard robot system is still a major challenge. Another direction is active mapping and next best view planning. This direction is closely connected to the computer vision side because the goal is still to improve the Gaussian representation itself. The robot actively decides where to move or where to look in order to increase coverage, reduce uncertainty, and reconstruct a better Gaussian splatting map. So here, the robot is not only using the map, and it is also part of the mapping process. This makes active mapping a natural bridge between Gaussian splatting and robotics. And the next direction is navigation, planning, and localization, which is the topic I am most interested in. Here, one important issue is anti-aliasing. In robotics, the camera used to build the Gaussian splatting map and the camera used by the robot at runtime are often not the same. The resolution, field of view, viewpoint, and even the camera model can change. But if we want to fully render the map in the way that the robot needs, we need one important assumption: that the rendered output should remain reliable even under different resolutions and camera models. This is exactly where anti-aliasing matters. Without proper anti-aliasing, changing the rendering resolution or sensor model can introduce artifacts, unstable observations, or degraded geometry. So if we want to actively use Gaussian splatting for robotics, especially for navigation, planning, and localization, we need to think seriously about rendering quality under different query conditions. In short, anti-aliasing is not just a graphics detail. For robotics, it is part of what makes Gaussian splatting usable as a reliable renderable map. Another direction that many people may be interested in is semantic Gaussian splatting and VLN using rich visual information. This direction is also very active on the CV side, so it is already becoming a crowded area. The main idea is to enrich Gaussian splatting maps with semantic or language level information and use them as 3D memories for embodied agents. But what I find interesting is that in many of these works, the planning part itself is still relatively conventional. For example, the robot may still use planners like RRT for motion generation, while the research focus is more on how to select the goal, identify the target object, or ground language instruction in a 3D scene. So in this area, Gaussian splatting is mostly used to improve scene understanding and goal selection, rather than to fundamentally change the planning algorithm itself. Another important direction is using Gaussian splatting as a simulation environment. There are already many works in this direction because Gaussian splatting can render realistic visual observations from reconstructed or generated scenes. This makes it useful for training robot policies, testing navigation algorithms, or generating data for VLA. I think this area has a lot of potential, especially when combined with generative AI. If we can generate or edit Gaussian splatting-based scenes, we can create diverse environments, tasks, objects, and visual conditions without collecting everything from the real world. So in this direction, Gaussian splatting is not just a map, it becomes a data generator and a simulation substrate for robot learning. To summarize, Gaussian splatting is quickly becoming popular in robotics, but most work still uses it mainly for mapping, reconstruction, and perception. If there is one sentence to remember from this task, it is this: photometric Gaussian splatting is not directly task-ready for robotics. I think many interesting research topics can come from this gap, turning visually rich Gaussian splatting maps into representations that robot can actually plan, localize, and act with. Thank you for listening to my presentation.